we are hopefully good to go with some more limit discussion. As always, can I just get confirmation in the chat that everyone can both see and hear me? All right, so now let me just see which problem set is this page opening on. What is this? What is this? Oh, finite limits. Okay, we'll get there soon enough. All right, let me try and remember where we were at. I closed all my pages and I don't remember exactly. We talked about finite limits, and we are just in the process of seeing all the variations, everything that we need to see to be ready for pretty much any question that could come our way. So far, I have learned that when I have a limit, there are certain ways I should look at it, certain things I hope for when I have some sort of limit. X goes to C, I have some function, and I'm trying to figure out, does this limit exist? If so, what is the limit value? Say whatever you can say. So first of all, I'm going to try, let's say here, try, that's a Y, to calculate f of C, meaning plug in the x value in question. Because for our functions, assuming that f of x is defined around x equal to c, if I can calculate a y value, the kind of functions we're looking at will be continuous at x equal to c, which means the limit is just the y value. The graph goes through that in one piece, nothing weird is happening. Yes, in advanced topics, there are strange, weird, and wacky functions that are technically not falling under this category. In this course, we're not going to see them, so I want to keep it as simple as possible. If that fails, then, and even in here, I can look at the form of the limit. Notice that if I look at the form of the limit, it is plugging in x into the pieces of the function. And if I can calculate a y value, then the form of the limit will be that y value. So it's sort of in here as well. But I don't have to look at the form when when plugging in the x value is going to work. There's no need to talk about the form, but it is the same thing in that case as well. Then now we saw that what could we really get? In the case of rational functions, which is mainly the situation that has the most interesting things happening. What can I get for a rational function? Now, I'm going to ignore the long-term case, infinity over infinity, but we can technically get infinity over infinity or 0 over 0. They're kind of the same. I can get a number, how should I write it? I'll write it as a k, non-zero over 0, or I can get 0 over some non-zero number. Non-zero k. Those are really the only combinations I could get, right? Now, I think we've seen 2 out of the 3 0 over 0 cases, but it might be worth just doing it all for review purposes, if nothing else. I think we'll still have time to do everything we need to do. There are only 5 examples. I think we're good. Let's review what we did last time. So I had an example, limit. It's good to review. It's been a weekend. Maybe you didn't get a chance to look at this at all. It might be worth reviewing. Okay, so I try plugging in 2, right? Doesn't work. Can't calculate a y value. So then I look at the form of the limit in the hopes that it'll tell me which direction to go. I then see, oh, it's 0 over 0. And if there are any questions about what I mean by the form of the limit, well, you should definitely ask. We've done this. There are videos, all kinds of stuff. So that is not ideal, but at least it tells me, oh, hold on, look at the specifics of the function involved. And in the case of a rational function, see if I can simplify and get rid of the bottom problem. So I will do that. Since I see, I can factor the top as the difference of 2 squares. Bottom is just an x minus 2, x minus 2. And then I see, oh, okay, well, one of the x minus 2's cancel. Oh, that's not bad. And the behavior of my original function is the same as the behavior of this. At least it's a simpler function, not the same function, but the behavior is the same. So I have technically a new limit question that I can look at, and I can look at the form of this limit. Well, the numerator now goes to 4, denominator 0, and you see that because I have a simpler function to look at, my case for the form is different. It's now this middle one, non-zero over something that approaches 0. I still can't plug in the 2. The function is still undefined there. But this form is much more informative. It tells me that the numerator stays constant while the denominator shrinks to 0. I think most of us agreed that this thing is going to blow up in size. Now, depending on everything else involved, it could be a plus or a minus infinity. I don't really care that much right now. The point is the limit does not exist. It's enough, in my opinion, knowing that it's an infinity. The size of the y value is blowing up. Yes, if I want to graph this, I want to know more, I'm going to have to know which one. But we'll have techniques at that stage to figure it out super easy. So I'm not going to worry about that right now. So as long as you have an infinity and say it doesn't exist, you're good to go. So I started with a 0 over 0, and I got an infinity. But the whole thing about 0 over 0 is that that form alone doesn't tell me what happens. If I look at the following limit, let's keep it 2, and I think we'll just flip them around. We'll just flip them around. Someone's motorbike in the background. Hopefully it's not too noisy. But let me know, I can close the door. So now I look at the form of this limit. I tried plugging in a 2, it doesn't work. Undefined. I look at the form, I get 0 over 0 again. Not ideal, but at least it tells me, look at the specifics of this function and see if I can simplify this and get rid of the bottom problem. Okay, so I'll factor it. I have 2 of the x minus 2's at the top. I have a difference of 2 squares at the bottom. And I see, oh, the x minus 2 problem, which was in the denominator. The x minus 2 was the reason I had a problem in the first place. I canceled that out. Which means that this function behaves the same as x minus 2 over x plus 2, the simplified version, which is not the same function. They behave the same around 2. And for the behavior, I'm never at 2. So I can look at the simplified version. This is technically a new limit. Look at the form of this limit. I have a 0 over 4. Let's see how I'm in the other case now. Where is it? Other case. 0 over non-zero. That is a much more informative form, which I can just read off if I understand the behavior of a numerator shrinking down to 0 and a denominator that stays constant. The whole thing is going to shrink to 0. And we ended by saying the limit exists because 0 is a number and I don't discriminate against any numbers. All right, so that's where we ended things last time, but it's good to remember anyway. Any thoughts or questions so far? Does everything make sense? Does it sound familiar? How do you feel? All right, big smiley face. I'm going to take that as a good sign. So we see that 0 over 0 can result in different answers, which is why it's called an indeterminate form, because we can't determine the answer just from the form alone. How did we get 0 over 4? You see what happens to just the numerator when x goes to 2. Well, the numerator is x minus 2. 2 minus 2, 0. So the numerator alone wants to go to 0. The denominator is x plus 2. Close to 2, it wants to go closer and closer to 4. 2 plus 2. So now I have an interaction of a numerator and a denominator that does different things. The numerator, what it does is shrinks down to 0. Denominator, no, it's going to happily go to 4. Never going to be perfectly at 4, but they're going to be so close. And that numerator is going to force the whole fraction to shrink down. The denominator doesn't balance it and try and counter it and try and do anything. So the numerator determines what the whole fraction is then doing. But initially I couldn't see it. Initially, technically, the numerator and denominator both go to 0. And then it's a question of how do they interact? How fast do they go to 0? What other things are they doing? Well, it turns out the numerator goes to 0 much faster than the denominator, and the denominator can't keep up. But I can't see it in the original form. Okay, one more example that we did write down, and I asked you to think about it, but let's be honest, you were going into the weekend. Who was actually going to think about this? I don't blame you. It's okay. We'll do it now. I look at the form of this limit because regardless, it's going to tell me something. I hope for a lot, but I'll take a little. When I plug in a 2 in the numerator, I get a 4 plus 2 is 6 minus 6, 0. And the bottom is also 0. So I can't say anything immediately. I need to go and look at the function, look at the specifics, and see if I can somehow clean it up, somehow clarify what's happening. And like in the rational function case, factoring, trying to cancel the denominator is often my best attempt. So can I factor the top? I hope I can. It's a plus 3 and a minus 2. Now please be aware that just because I have 0 over 0, just because I can factor the numerator doesn't mean I will always cancel something. Look at this first. Okay, the first one, bad example. I still canceled something. I think we're going to get to something where it's not necessarily the case. And even if I can cancel something, I might not cancel out the problem, making this whole thing undefined. There's absolutely anything can happen. Maybe I'll do a little example. I might have. Let me just check. I'm going to do 17 and 18, and they might. I think they're going to show what I mean. So let's just wait for those. So now I see. Ooh, yay! I can cancel the x minus 2's, and the x minus 2's were the problem. Well, there was only one in the bottom. So the behavior of this original function is the same as the behavior of x plus 3, which doesn't have any problem. It's a polynomial. It's great. Plug it in. It's defined everywhere. It's 5. 2 plus 3. I can look at the form here, but in the case of a continuous function, the form is exactly the same as just plugging it in. And it's a little unnecessary to double up with something that's overkill. Of course, limit exists. So, to sum up, in all these cases, I had 0 over 0. But literally anything can be the answer. And I don't know until I look at the specifics of the function. That is the lesson here. I'm always so close to banging my head against the table when I still see in tests someone gets 0 over 0 and then they say it's equal to 1. And I'm like, where were you for the last months? That is not how things work at all. I am just trying to indicate how pieces behave relative to each other. Actually, no, individually, not relative to each other. And if I get a 0 over 0, well, that can mean many, many different things. Let's go back to our problems. We haven't done. These should be in the problem book, but they're not, so I still had to add them. Very important to see. But let's go something that is in the problem book, 3.2, number 17. Let's have a look. I don't want that. I want this. 17. Where are you? I guess I shouldn't scroll so fast. Slow it down. Slowly. Reveal 17. Boom, there it is. Okay, now I just copy that. Limit. Once we understand how to look at these things, I feel like I should apologize. There isn't really much mystery here, but we'll try and see if we can come up with some mystery. X squared minus 1 over x cubed minus x. Right? Yeah, pretty sure. Okay, try and plug it in. It's not going to go well. Your calculator says error. So I now have to figure out, where does that error come from? Why is this function not defined at 0? Could be a little hole, could be a vertical asymptote, could be, well, really, those two. So I get plugging in 0 at the top gives me -1. Plugging in 0 at the bottom gives me 0. What does this tell me? I claim it tells me everything. Well, enough. Almost everything. If I have the top going to a non-zero constant, the bottom shrinking down to 0, there is only one way this is going to happen. The whole thing blows up. In this case, a negative infinity, but if you want to say plus or minus, I'm not going to care. I understand our tools are limited, and finding out which infinity is not the goal right now. It's an infinity right away. I don't have to do a thing. Limit, I did my work. It's in the form. Limit does not exist. If you want to factor this, top one goes to x plus 1, x minus 1. Bottom one, I can factor out an x. And then I have x squared minus 1, which is going to be the same. I'm doing all this work. I'm not getting rid of the problem. The form tells me I will never get rid of the problem. There's a vertical asymptote. It's going to blow up to infinity. The form already tells me all of that. Why would I go through all the factoring work when it's not going to get me anywhere? It's silly. It's all silliness. The form, ideally, tells me everything I need to know. Now, if the form was 0 over 0, then there is a chance that the bottom problem could feature at the top. There's a chance they could cancel. I need to go explore that. But if the form isn't 0 over 0, why would I care to do any more work? Back it up. Oh, so close. My undo can only go so far. Don't want to see any of that nonsense. I don't need it. If you want to be busy and make work for yourself, go nuts. I don't need it. I hope for the best, but the 0 over 0 indeterminate forms tell me to now go dig in the function. Anything else, and I'm good to go. I'm looking for the path of least resistance here. Why make work for myself? But there's a requirement of some understanding. First of all, what we mean by the form, how to use it, what we're saying and what we're not saying. People don't understand what we're saying, and more importantly, what we're not saying. But if you do understand what we're trying to do and what this can tell you, it's really extremely simple. Well, you hope for a form that's not indeterminate, right? Then you're golden. But if you get an indeterminate form, at least you know, okay, let's go dig in the function and see what we can come up with. Oops. So not all secrets are revealed, but I still hope for the best. And honestly, in 2 out of the 3 cases, it's going to be extremely straightforward. Now, there are exceptions, but let's just do this one question. I'll do 18. 18 is over there. Limit x goes to -1. Finite, whoopsie. Finite limit. What's the limit? X squared minus 1. What's the function? X squared plus 1. What do I do first? Nothing. I do nothing. I wait for the instructor to tell me. Well, eventually you have to. You have to, when faced with a question, know what are my options? What do I try first? When that doesn't work, what do I do? And so on. I can totally go to the form. Yeah, absolutely. I plug it into the top. I get 0. Right? -1 squared is 1 minus 1, 0. I plug it into the bottom. -1 squared is a 1. Plus 1 is a 2. And now I'm laughing. Because anything with a numerator and denominator that has individually this kind of behavior is going to go to 0. There is no other way. The denominator is not keeping up with the shrinking down of the numerator. It's doing its own thing. It's saying, I'm off to 2. You do whatever you want. The numerator says, sweet, I will shrink this whole thing down. And no one will stop me. Now, you could have just plugged in a -1. You get a y value. And because it's a rational function, wherever it's defined, it's continuous, everything's good. You'll get a 0. But the form does that anyway. So there's no real need for it. It's really up to you. I don't care. The form is technically overkill when the function is continuous, but it's not going to give me different information. So there's no downside, really. There's no downside to the form. Apart from technicalities, which we have to watch out for. I do have to emphasize this. Now we're getting into the technicalities. There aren't many. That's the good news. But there are some. That is the bad news. Even at this basic level, there are some technicalities that we very easily forget. Whoops, no, that's not at all what I'm doing here. Where's my page here? Nope, that's not it either. Oh, it's up there. There we go. We do forget this. There is this requirement that for this limit behavior question to even make sense, to be asked, we need this. We need f, we need the function to be defined around my x value in question. Now, if I'm dealing with a rational function, then I know, or a polynomial, I know everything's good anyway. I don't need to really worry about whether or not the function is continuous apart from its possible vertical asymptote, right? Because this is essentially built on my basic function. I know if I stay away from the vertical asymptote, it's a one-piece function, right? I jump over that, sure, but apart from that, there are no issues with this function. They're it's very close to polynomials. Or if I have a polynomial, I know there's no issue. So I very quickly, very easily get encouraged by way of my examples to forget this box. And for the most part, I'm safe to do that because the functions are very simple functions. But what are our basic functions so far? It's in my head. It's the library. I have them. I have all my basic polynomials. Great. No problem at all. I have my basic rational function. Sure, apart from a vertical asymptote, which the 0 over 0 form is going to point out, no problem. But I have other functions, like the square root function, which does present a teeny tiny problem. Teeny. I just need to be aware of it. So, and it's really only for our purposes. I'm trying to think. It's really only the square root function, except if it's some weird made-up function, which we'll see later. Okay, let's have a look at this guy. What would you say is that answer to that limit question? No, it's a safe space. You can say whatever you want. What would you say? You get this, pop quiz, right now, you have 2 seconds to respond. Of course you're going to say 0. Everyone wants to say 0. However, unless I keep in mind, let's say it like this, unless I keep in mind what this limit is really saying, I'm going to give the wrong answer. This is asking for the behavior, of course, a very simple function, it's in my library, of my square root function as x, I'll write it down, gets closer to 0, I'll say it like this, from anywhere around 0. It's the same as this. I need to be in my original behavior question. I need to be coming at the x value from anywhere. But this function and its graph isn't defined anywhere. It's only defined on x greater than or equal to 0. So in this special case, it's very special, it's very specific, where I am interested in what happens at 0, I want to be coming towards 0 from anywhere and ask, how does the graph behave? Now this question doesn't make sense because there is no graph here to get closer to 0. I can't travel along anything on the left side because there is nothing there. It is a technicality. It's a feature of this square root function only being defined on half the x values. And for that reason, because of the definition of the limit that we are hiding a little bit, this does not exist. Because the question is not fitting the function. The question doesn't make sense. However, if I ask for the behavior as x goes to 1 of the square root function, totally fine. Let's put 1 up there to exaggerate. I can travel towards that point or that x value from either direction, no problem at all. 1, it exists. Nothing is strange. It's only because the square root function has this endpoint that the original limit question didn't really think about that. It thought about polynomials and rational functions and nice things that sort of has almost all x values, the function almost defined for almost all x values. I always have a window around the x value. I can approach from either side. The question makes sense. Everyone's happy. Now we look at this more special square root function that has an endpoint. And now the question doesn't make sense, unfortunately.
Please remember to click the like button if you enjoyed the video, and to subscribe if you want to be notified of more videos. Thank you.